Hello. So in the last class, we have defined the outer measure for a set A. So n star of A is defined as infimum of summation length of I, and where the set A is covered by the collection of sets I. So A is contained in unit I. So this is how we have defined the Lebesgue outer measure. Now we will see a proposition concerning the outer measure. So the proposition, so we will see two propositions. So proposition 1 is, so the proposition 1 states that the outer measure of an interval is its length. An interval is its length. So we will show that measure of an interval will be equal to length of the interval. When you take intervals, there can be finite intervals or infinite intervals. അതുപോലെ intervals closed ആവാം, open ആവാം, and either of the sides may or may not be included. Semi-open, semi-closed ആയിട്ടുള്ള interval. So for each case, we will prove that. So when we take n star of I, so we show that is equal to length of the interval I. So we will do the proof of three. There are three cases. The first case is when I is a finite closed interval, and the second case is when you have an open or when you have a finite interval which is open or semi-open, and the third case is when you have an infinite interval. So in all the three cases, we will show that its outer measure is same as length of the interval. So let us look at the proof. So first case 1. So case 1, we assume that our interval I is closed interval, and we need to show that its measure, outer measure, is equal to its length. So assume that case 1, assume that I equal to closed interval AB is a finite closed interval. Then what we need to show that is, n star of I will be equal to length of I, which is equal to b minus a. So length of this closed interval will be equal to b minus a. So this is what we need to show. Now for any n belongs to n, so if you take the closed interval AB, closed interval AB will be contained in an open interval a minus 1 by n b plus 1 by n. So if you have any finite interval of this form, so closed interval AB will be always contained in an interval of the form a minus 1 by n b plus 1 by n, where n belongs to n. So here you have an open set which is containing your closed interval AB. അപ്പോൾ ഇതെന്ന് പറയുന്നത് നമുക്കൊരു open cover ആണ് കിട്ടുന്നത്. So you are getting a covering of your interval I. So we have I equal to closed interval AB. So therefore I is contained in a minus 1 by n b plus 1 by n. So therefore this interval a minus 1 by n b plus 1 by n is a covering of the interval I. So therefore n star of I, so by the definition of measures, n star of I will be less than or equal to length of this interval. Okay, so since closed interval I is contained in this interval, so if A is subset of B, measure of A will be less than or equal to measure of B. So this will be less than or equal to length of A minus 1 by n to B plus 1 by n. So that will be equal to, so the length will be b plus 1 by n minus a plus 1 by n varum. So that will be b minus a plus 2 by n. So therefore m star of I will be less than or equal to b minus a plus 2 by n, and this inequality will hold for all n belongs to n. Now upon taking limit as n tends to infinity, again this inequality holds, so we will get m star of I less than or equal to b minus a. So since this holds for all n belongs to n, we may take limit as n tends to infinity, and we get, so we will get m star of I less than or equal to b minus a. So as n tends to infinity, limit of 2 by n will be 0, so that will be equal to b minus. So we will be getting m star of I less than or equal to b minus a. So call this as equation 1. So we need to show that m star of I is equal to b minus a. So we need to now show that m star of I is greater than or equal to b minus a. So then we can conclude that m star of I will be equal to b minus a. So next we need to prove that. So we need to prove that m star of I is greater than or equal to b minus a. So we will prove that using the definition of m star as follows. Let's take, so let us consider the sequence in. So let this be a countable collection of open intervals such that it covers I. So let sequence in be a countable collection of open sets such that I is contained in union over I. So union in, that covers I. And now നമ്മുടെ സെറ്റ് ഐ എടുത്തിരിക്കുന്നത് that is closed interval. I എന്ന് പറയുന്നത് closed interval ആണ്, closed interval AB ആണ്. So that is closed and bounded set. Finite interval ആയതുകൊണ്ട് closed and bounded ആണ്. So therefore by Hailey-Borel theorem, every covering will have a finite subcover. So when you take any open covering of a closed and bounded subset of R, then it will have a finite subcover. So then by Hailey-Borel theorem, every open cover has a finite subcover. So every open cover of I has a finite subcover. So this is because since I is closed and bounded. Now for നമുക്ക് നമ്മളൊരു കൗണ്ടബിൾ കളക്ഷൻ ഓഫ് ഓപ്പൺ സെറ്റ്സ് ആണ് എടുത്തത്, ഓപ്പൺ ഇന്റർവൽസ് ആണ് എടുത്ത IN എന്ന് പറയുന്നത്. അപ്പൊ അതിൽ നിന്ന് നമുക്കൊരു ഫൈനൈറ്റ് സബ്കവർ കണ്ടുപിടിക്കാം. ഓക്കെ, സോ ലെറ്റ് മീ ടേക്ക് my values a and b to be. Okay, അപ്പോൾ there will be a finite subcover. A finite subcover that will be some open intervals. Okay, അപ്പോൾ നമ്മൾക്ക് I is contained in union of IN since closed and bounded ആയതുകൊണ്ട് here you can find a finite cover. അപ്പോൾ finite coverലുള്ള സെറ്റ്സ് ഞാൻ A1, B1, A2, B2, AN. So let me take my sets to be of this form. So from the figure you can see that we have A1 less than A2, then less than B1 less than A3, less than B2 less than A4, less than B3, etc. the last value will be Pn. Now the sets A1, B1, etc. An, Bn. So the sub collection of sequence In. So therefore, when you take summation of length of In, അപ്പോൾ In ന്റെ sub collection ആണിത്. Summation of length of In will be obviously greater than or equal to length of the set A1, B1 plus length of the set A2, B2 plus etc. length of the set An, Bn. Now, since this is an interval, the length will be equal to B1 minus A1. Then length of A2, B2 will be B2 minus A2 plus etc. Bn minus An. Now, this will be greater than or equal to Bn minus A1, which you can see from the figure, so therefore it will be greater than or equal to B minus A. Okay. Therefore, we are getting summation over length of In, and that will be greater than or equal to B minus A. Now this gives infimum of, and this will hold for any covering. So infimum of summation of length of In will be greater than or equal to B minus A. So this means this is going to be m star of I by definitional measure. So m star of I is greater than or equal to B minus A. Now we already got that m star of I is less than or equal to B minus A. So combining both, so we will be getting m star of I is equal to B minus A. So if I is equal to closed interval AB, so we will be getting m star of I will be equal to length of closed interval AB, which is equal to B minus A. So when you have a finite closed interval, then its outer measure will be equal to length of the interval. Now we need to look for the next case. So in case 2, we will be assuming that I is an arbitrary finite interval. അതായത് ഓപ്പൺ ആവാം അല്ലെങ്കിൽ സെമി ഓപ്പൺ ആവാം. So in that case, we look for whether m star of I is equal to length of the interval